All right, good morning, even though you're probably looking at this in the afternoon. What we're going to look at today is how to predict whether reactions will go or not. And we're going to focus on single replacement and double replacement. And each of those reactions has a totally different method that we look at. Now, the single replacement, I'm just going to show you the materials in the reference tables that are used. We're not going to do any exercises with that. It's easy to look up and do when you need it. It's not really something you need to practice. Double replacement, we're going to do a little bit more. I'm going to show you how to write the projected products, the potential products, and then what to look at to test whether or not the reaction is likely to go, and then follow up by writing the formula reaction and balancing it. So again, we're going to focus on single and double replacement. Single replacement, if you remember, is always an element plus a compound going to a different element plus compound. It can be a halogen replacement, the halogens being fluorine, chlorine, bromine, iodine in that group on the far right of the periodic table next to the noble gases. Here, fluorine, and they're all diatomic. Fluorine comes in, replaces chlorine. That's a halogen replacement. The other kind is a metal replacement, where one metal is an element but ends up being in a compound. One metal was in the compound, ends up being an element. Double replacement is always two ionic compounds, anion, cation, anion, or it's an acid and a base, and I'll show you a little bit more about that. So here we have silver nitrate, metal cation, polyatomic anion, and magnesium bromide, metal cation, nonmetal anion, and they swap. Each cation gets the other anion, basically, swap partners, but it's two ionic compounds reacting to form two other ionic compounds, or an acid and a base. Acids, the acids that we will consider, all the formulas all begin with H. H is a funny element. It can act like a metal or seem to take the place of a metal in formulas, and we'll talk more about that later. The bases that we will talk about are all metal hydroxides. So that hydroxide polyatomic ion signifies that you're talking about a base. So if we have an acid and a base, they react to form an ionic compound, which we always refer to as a salt in an acid-base reaction. And the H from the acid combines with the OH from the base and gives us HOH, which we also write H2O, i.e. water. So the products of the reaction of an acid and base are water and a salt. Any acid and base reaction, we say it goes because it forms water, which is a new substance. Even though it's in water, these are all solutions in water that we're talking about here. It has formed water, so that we call a reaction that will go. So if you see acid and base, then the criterion is met. The reaction goes. All right, so we are going to use information in the reference tables, of course, because that's what we do in this class. So for single replacement, we have something called the activity series. All right, and I have, there are two activity series, one for halogens, one for metals. Here we have the halogens, and over on the right, I've got an image of part of the periodic table with the halogens highlighted, fluorine, chlorine, bromine, and iodine. You can memorize this part if you want. If the element in the reaction is higher on the periodic table or higher in the activity series than the one that is in the compound, it will replace it. Higher in the series replaces lower in the series. So fluorine will replace chlorine, but not the other way around. Chlorine cannot come in and knock the fluorine out of lithium fluoride. So we say no reaction. Activity series of metals. I'm going to click this. This is what a reaction, a single replacement reaction of a metal looks like. One metal is part of an ionic compound that is dissolved. It's a solution, it's dissolved in water. The other metal is an element. And for metals, an element is a solid metal. So it is submerged in the solution. And we see a plating out of the solid metal that was in the solution. And at the same time, the solid metal we put in becomes part of the compound. In other words, it dissolves. And we will see at the end that this thing turns blue. So any element in a proposed reaction that is higher up will replace the metal in the compound. So there you have a whole bunch of, that was silver and copper. We have a whole bunch of solid silver deposited at the bottom, and you can see the blue color, and that bluish green color is very typical of copper ions in solution. So what we're seeing here is that copper metal, silver was in a solution, silver nitrate was in a solution, and copper metal was placed in it, and the copper replaced the silver. So let's see if the copper, here's copper, and here's silver. So copper is above silver, and the rule that they're saying is something up higher up on the series can always replace something lower in the series. They're talking about the element replacing the other metal in the compound. Example, zinc is widely used to protect steel in a process called galvanizing. It can be hot dipped, it can be electroplated, but it's put on the surface of the steel. It's a way better protection than paint, because if you get a chip in your paint, you'll get a pit, but if you get a hole in your zinc, the zinc will still protect it. It's called a sacrificial coating because the zinc in a single replacement reaction replaces, if the iron starts to form an oxide, what we don't want is rust. Rust is iron oxide. The iron starts to form an oxide. Here comes the zinc. The zinc replaces the iron in the oxide and pushes that iron back to being solid iron. And you can see on this series that here is zinc. It is above iron in the series. And so that explains why the zinc will always replace the iron, leaving the iron as solid, does not go the other way around. All right, so double replacement reactions. This is what we're going to focus on and what your worksheet is on today. So double replacement is the change partners reaction. It's always two ionic compounds reacting with one another, or an acid and a base, as I showed earlier. So we are going to predict the products. Then we are going to apply criteria to see if the products are actually formed, i.e., does the reaction take place? Does it go or not? And then if we decide that it does go, write and balance the formula equation. So this is mostly putting together skills that you've already used, because we're going to predict products using the solubility tables. We're going to predict products first, then we're going to use the solubility tables. So it's easiest to work with the names. Remember, these things are ionic. The name is cation, then anion. We're going to change partners. The potential products have both cation and anion. We always say the cation first. So for example, we have a reaction between calcium nitrate and potassium phosphate. We want to switch those partners around. Calcium and potassium are still going to be written first in the products. So the first of the first and the last of the last is calcium phosphate. And then the first of the last with the last of the first gives us potassium nitrate. So calcium nitrate plus potassium phosphate gives us calcium phosphate plus potassium nitrate. So next we test to see if products are formed. And what we use to see if products are formed are the solubility rules. Because if we just have two ionic compounds, we dissolve them in solution, we have, how do they dissolve? The ions separate, right? We have ions in solution. So solution in one hand has two different ions, one positive, one negative. The solution in the other hand has one positive, one negative. We pour them together, we have a whole bunch of ions. If all the ions just stay in solution, we say no reaction. But if one possible new combination of the four ions is insoluble, it will form a solid right out of that solution. We call that a precipitate. And then we have a separate product that has formed, so we say that that reaction does go, that does make a product. And we're just going to apply the solubility rules from the reference tables to the potential products that we wrote and see if one or the other of them is insoluble. So let's find the products to our previous reaction in the solubility rules. I will move myself out of the way here. So, all right, calcium phosphate was our first product. So calcium, we don't have the periodic table in front of us, but it's in group 2. Group 2 are only in here as exceptions. So let's start by looking at phosphate. Most of the familiar polyatomic ions can be found in this table. So we'll look at the soluble side: nitrates, acetates, ammonium, chlorides, bromides, iodides, fluorides, sulfates. Okay, no phosphate. Over here, insoluble, all carbonates and phosphates with exceptions. Okay, so phosphates are insoluble unless calcium is one of these exceptions. Group 1, no, it's in group 2, and ammonium. So calcium phosphate is going to be insoluble. Now, there cannot be more than one insoluble product, just because if you've got the kind of ions that make things soluble in the reactants, they're going to combine and be soluble in the products. But let's look at potassium nitrate anyway. So potassium, remember, is in that first column of the periodic table, group 1. And on the soluble side, everything in group 1 is soluble. And not only that, look at nitrate. All nitrates are soluble. So potassium nitrate is about as soluble as it can get. All right. Testing for products, the other possibility is the reaction of an acid and a base. We say that gives water and a salt. Now, salt is just a word for an ionic compound. Salt is kind of our prototype ionic compound, the crystals, the brittleness, the solubility in water, and ability to conduct electricity and so forth. So we refer to all ionic compounds as salts. The ions that were dissolved in solution are still in solution. If we evaporated the solution, they would crystallize out. But water is a new substance. Remember, the acid and the base reacted together. The hydrogen from the acid joined with the hydroxide from the base. H plus OH gives H2O. So all acid-base reactions will go. So we had sulfuric acid plus potassium hydroxide. The formula for sulfuric acid is H2SO4, potassium hydroxide, KOH. The salt we make is K2SO4, and we get two waters, hydrogen from sulfuric acid combining with hydroxide from potassium hydroxide. Metal hydroxides are bases. Acids, on your worksheet, you have the names and they say acid, and I also gave you the formulas of the acids because we haven't studied those yet. All right, so then write and balance the formula equation. This is using skills you already have. For writing formulas for ionic compounds, you need to identify the names of the ions and then use the charges of the ions to figure out what the formula has to be to make it charge neutral. So we have calcium nitrate plus potassium phosphate gives calcium phosphate plus potassium nitrate. So we're going to find calcium, we're going to find nitrate, we're going to find potassium, we're going to find phosphate, and then we're going to see how they have to combine. So calcium nitrate, we have a +2 and a -1. Potassium phosphate, we have a +1 and a -3, so we need 3 potassiums. And then we've got the same ions again. Calcium phosphate, we got +2 and -3, and potassium nitrate, +1, -1. So these are our formulas. We still want to balance it. This is putting all the skills that we've worked on recently together. And if you remember, I said that a good place to start balancing a double replacement reaction is to look for the one formula that has the biggest charges. And in that case, it's going to be calcium phosphate. And you saw this when you had to find the formulas. Calcium is +2, phosphate is -3. So let's look at this. We need 3 calciums. Let's put a 3 over here to give us 3 calciums. We need 2 phosphates. Let's put a 2 here to give us 2 phosphates. We only have one thing that still needs a coefficient. We have a 2 in front of this times 3 potassiums in the formula gives us 6 potassiums. We have a 3 in front of this times 2 nitrates in the formula gives us 6 nitrates. If we put a 6 in front of this, that is going to make potassium and nitrate come out right. And that's that. I hope that that's enough for you to understand what you have to do on the worksheet. If not, please come by during my virtual office hours from 2 to 4 this afternoon. Thanks. Uh-oh.